Number 4. Wes, tell me something about differences between those.
They all have different amounts of moons circling them.
Yeah, so the moons are a big difference. Jovian planets have lots of moons. Terrestrial planets have not that many. Trayvon, what's something else?
Jovian planets have rings. Terrestrial planets do not have.
Yep. Okay, you may not know this. Saturn is not the only one that has rings. In fact, all of them have rings. Now, they don't have very large ring systems, but they all have rings. Jupiter has a fairly small one. Uranus's are pretty sizable, but it's far away, so it's hard to see. Neptune's are very minimal, but Neptune does have rings also, so they all have rings.
I was going to say another one. I don't know if this was on the paper, but wind speed is another one of them.
Yeah, we're talking about differences between the terrestrial planets, and not all of them have thick atmospheres, so that's kind of hard to measure. But you're right, the different Jovian ones are different.
Spot.
Yeah, Riley? Yes. If you think about the PowerPoint image I had here, you can see these are more spread out. Now, this is not to scale, but these are more spread out from each other than what the terrestrial ones are. So the spacing between them is different. Good. Brea, what's something else?
Terrestrial planets are small, rocky, and
Yep. So terrestrial, they're small, they're rocky, they're dense. The Jovian planets are none of those things. They are very light. Well, I shouldn't say light. Their density is low. They're made of gas, and they are really large, like really large. Hence why they're called gas giants.
Wait, so that's just straight up gas?
Yep.
What about the core?
So that's a good question. We don't exactly know what the core is, although the common theory is that it's a liquid version of the gas. So like the center of Jupiter is probably liquid hydrogen. And possibly solid hydrogen, depending on what the temperature and density is like there. But it's still hydrogens and nitrogens and heliums and that kind of stuff.
So if you were to go there, you'd poof right through?
Yeah. Maybe not all the way to the other side, but you'd be able to go into the planet. Yeah. It'd be a bad idea, but you could do it.
Cool.
It would be cool. It wouldn't last long, but you could do it. Good. So these are kind of the big ones. Some other differences. We talked about the rings, talked about the surfaces. Another one is magnetic fields. Not all the terrestrial planets have magnetic fields, and the ones that do are fairly small, with exception of Mercury's is pretty strong. But Mercury's kind of like a magnet anyway. It's close to the sun. It's got a lot of iron in it. But the Jovian planets have really strong magnetic fields, which is why we think the core is liquid. Because we think it's a lot of really fast-moving charged particles in the core, which would be in a liquid form. It's still going to be the same materials. It's not like Earth's surface, which is different than what the core is. We think it's the same materials, same elements, but a little bit different. So that's another one there. Talked about the spacing, talked about that. And just to kind of reiterate the point, you, in theory, should be able to go all the way through Jovian planets from one side to the other. In theory. Again, that's not saying that you actually could. We don't know exactly what's in the core of these, but that's the idea. Okay? Nice. All right, let's jump back to the PowerPoint here. And we need to make a list of observations about the solar system because, let's be honest, we want to know how the solar system came into existence. And we want to know what it's like. Like, honestly, the whole point of science is to explain things. So one of the most important things to be able to display is the solar system because it makes up everything that we know about our immediate vicinity in the universe. So a couple of things about it. So first of all, nearly everything rotates counterclockwise. Nearly everything lies flat on the plane. And that's called the ecliptic, by the way. And if you want to see a picture of what I'm talking about, on the very front page, if you look at that second picture down in the reading, that's what I'm talking about. All of the planets are relatively in a flat line with each other. You can see there's one slight exception, that's Mercury. That's because Mercury's too close to the sun. It's not Mercury's fault. It's just too close to the sun. Okay. Third observation is nearly everything follows almost circular orbits. The exception are comets. And some of the dwarf planets have fairly elliptical orbits. And the composition. Inside the asteroid belt, things are rocky. So this is what Max was talking about. Outside the asteroid belt, things are gaseous. And outside the Kuiper belt, things are icy. So it goes rocky things in close, gassy things in the middle, icy things out near the edge. So, we need to come up with a theory that explains these things. Because no theory is any good unless you can explain what you observe. And these are the main observations that we make. I combined a couple of them together. Your reading has a few more listed there. Your reading has 8, but I kind of combined some of them together. All right, so purple are the things that I just listed. The things in white are the explanations. So as objects undergo gravitational collapse, they rotate. Okay, you've all seen this before. If you fill up a sink with the drain plugged in and you pull the plug out, the drain starts rotating around. That's what things happen when they collapse inward on themselves. As things collapse in, they begin to rotate. So that explains why everything rotates counterclockwise, because that's the direction it would have rotated if our solar system started to collapse on itself. So we said there had to be some sort of collapse. Okay, the second thing is as objects rotate, they thin out and they flatten. If you've ever been on a merry-go-round, you know that if you get going really fast on the merry-go-round, you feel like you're getting pulled out from the center. And you get pulled out from the center in a straight, flat line. So as things rotate, they flatten out and they thin out. So there should have been some rotation, because that's part of why the solar system is thin and in the same line with each other. So if things rotated to begin with in that first one, then they would thin out and they would flatten after that. Third one, as objects thin out, they do so uniformly. So almost everything follows circular orbits, so all the orbits would be about the same because it would thin out evenly. And lastly, the composition. Rocky things survive near the sun. Gassy things survive further out. Icy things only survive near the edge. And that has to do with the heat and the temperature. Okay? In really high temperatures near the sun, only rocky things could sustain that temperature without evaporating. Okay? Further out, gas things could maintain their condensed form. And near the edge is the only place where icy things could contain their normal form. Okay, so how was the solar system formed? Now, I got an image for you. It's got a lot of words. The words are very small and hard to read. If you want to come back to it, you can do that. Or if it would help you to pull it up on your own, it is up on Schoology. But I'm going to walk you through it and talk to you about what the important parts are. Okay? So you can just follow along with me if you find that easiest. See, there's words and they're very tiny. Here's the steps that you should know. So this is 6 now. Let me see where we are on the timer. Yeah, let's keep going. All right, 6. So here are the different steps that happen. So step number 1, the solar system was a giant ball of gas. Step number 1, giant ball of gas. Rowan, keep the phone up for me. Giant ball of gas, step 1. Step 2, something happens that makes the giant ball of gas collapse. Probably the explosion of a nearby star. So step 1, giant ball of gas. Step 2, giant ball of gas begins to collapse. Okay, as it collapses, it starts to rotate. So it starts collapsing in. As it starts collapsing in, it begins to rotate around. As it begins to rotate around, it starts to thin into a disk, and it starts to spread out from that disk. So, giant ball of gas. Something happens, gravity starts collapsing it in. As it starts collapsing in, it starts to rotate, and it starts to thin out. Then something happens. Bam! That's what happens. What happens is fusion. And this is probably the most important step. So step 1, ball of gas. Step 2, gravitational collapse. Step 3, rotation, flattening out. Step 4, fusion. Nuclear fusion. The sun turns into an actual star. Before, it was just a hot ball of gas that was kind of glowing a little bit. Now it's actually producing light. Okay? So before it's called a protostar. Protostars have light, but they're not producing light using fusion. They're just producing light from heat. They're kind of like giant light bulbs. Okay? As opposed to producing light by doing actual fusion process, which is what the sun does. Okay? So that's the 4th step, and that's the most important one, because once that happens, everything gets pushed out to its starting places. So step 5 is the solar system gets pushed out to its current location. And step 6 is now. Everything looks the way it does. The reason the planets formed is there were areas of slightly more dense material when everything got pushed out. And those areas of slightly more dense material turned into the planets. Turned into Jupiter and Saturn and those kind of things. So to get to Max's question about why do they look differently, that came to that last bullet point in number 6? That last thing about, or not number 6, and number 5. That last thing about the composition. So the things that were left over when the sun started fusion were rocky things close to the center of the sun, which is where you got your terrestrial planets from. The things that were left over in the middle that got pushed out from the center or gassy things, and gassy things could form